Okay, this video is going to be the first in my series explaining concepts in Calculus 1. And so we start Calculus 1 with this idea of a limit. And so we look at the graph of a function, I think is the best way to kind of start this. So let's look at this graph over here, this guy over here, f of x. So we notice that f of x is one kind of solid curve. There's no breaks in it. And so it's really natural for us to kind of imagine that there's a guy. He's walking along this curve here, and he keeps walking, and he wants to get to where x is equal to, we'll say 6. So he's walking from the left, all the way up to 6. And we say that eventually he gets to this x value 6 and this y value 2. So he reaches the point 6, 2. Again, if he were walking from the left, from the right, he was approaching from the left before, he starts walking from the right, well, he approaches the same point, right? We get there no matter which way we approach from. This concept of him walking towards this and eventually arriving there is called a limit. But he doesn't necessarily need to arrive there for there to be a limit. So what I mean by that is, let's consider this function g of x. So let's say my guy is walking along, and he wants to get to the x value c, and he's kind of approaching the y value k, right? So this point, it has y value k, but notice that he can't actually step on this point because there's a hole there. He'll fall through. Now similarly, he could walk from the right here, and he would still approach the x value c, and he would still approach the y value k, but he would never be able to quite get there. Just because there's a hole right here, he would fall through. Our idea of coming from the left and from the right, approaching this point, is called left-hand limit and right-hand limit. And we say if they're equal, that the limit of our function is the value that we would expect it to take, or where our little guy would want to go if he were to make one more step, right? So if we'll say f of x approaches L, so our idea, right, is if I have a function f of x, and let's say this is the value L, and this is x, for some x, and this is f. It approaches L from the left. We write that the limit, let me do this in a different color. We write that the limit, we'll say this is some value c, as x goes to c from the left, we use a little minus sign to indicate that we're coming from the left, so that's like our little guy walking up from the left, of f of x is equal to L. Okay? Now, if f of x approaches L from the right, we would write that the limit as x goes to c of f of x from the right, we use a little plus sign to indicate that, is equal to L. So that is equivalent to our little guy walking up to our point from the right. Okay, so we're approaching from the right. So that's this right-hand limit here. And we say that the limit as x goes to c of f of x equals L if the limit from the right, we'll start from the left. The limit from the left of f of x is equal to the limit from the right of f of x, and both of those guys are equal to L. So we're saying no matter how our guy approaches this point, he'll still get to the value, in this case, k. So we'll still get to the same value, okay? We call that a limit, so that's our idea. And we have some properties of limits. So suppose that the limit as x goes to c of f of x equals L, and the limit as x goes to c of g of x equals m. So f and g are approaching L and m as x goes to c, right? So think about our little guy walking on these curves. So some properties of that are, if for a constant k, so k might be 2, 3, pi, 5, just some number. The limit as x goes to c of k times f of x is k times the limit as x goes to c of f of x. Or in other words, it's just k times L. Okay. Similarly, the limit as x goes to c of f of x plus g of x will be the limit as x goes to c of f of x plus the limit as x goes to c of g of x, which are just L plus M, right? Those are the limits. And it makes sense, right? If you have the limit of a sum, you should have the sum of limits, okay? Similarly, the limit as x goes to c of f of x times g of x, the limit of the product is the product of the limits, so it's the limit of f of x times the limit of g of x, which is just L times M. And finally, we assume that M is not 0, because otherwise this would be undefined. This is the limit, so the quotient of limits is the limit of, the limit of a quotient is a quotient of the limits. So we have the limit as x goes to c of f of x over the limit as x goes to c of g of x, which is L over M. Okay, so let's kind of apply these to some problems now. So I want to look at f of x is equal to x squared plus 3x plus 5, and I want to find the limit as x goes to 2 of f of x. Well, that's going to look like the limit as x goes to 2 of x squared plus 3x plus 5, and that's going to be the limit as x goes to 2 of x squared plus the limit as x goes to 2 of 3x plus the limit as x goes to 2 of 5, right? Because I can break my limits across the sum. The limit of a sum is a sum of the limits. We said that here, okay? Now, from here, I think about my curves, right? So, for example, x squared. So my little guy, if he's walking, he'll just approach 2, right? It's fine. So I can just go ahead and plug in 2, because he will get there. There's no issue. There's no discontinuity, or I shouldn't say discontinuity. There's no holes or gaps or jumps or anything like that. So I can just plug in 2 for x, and there's no problem. So this would be 2 squared plus, same thing here, I have 3 times 2. And then there's no x here, right? So the limit as x goes to 2 of 5 is just going to be 5. It doesn't matter where x goes. It's 5 always. So plus 5. So this is going to be 4 plus 6 plus 5, which is going to be 15. So that is our answer there. Okay, next let's look at the limit as x goes to negative 2 of g of x. So this is going to be the limit as x goes to minus 2 of x squared minus 4 over x plus 2. And now our first thought may be, just like the first one, to just start plugging in values. And you'll kind of see that there's a problem with doing that. So if I just plug in values, I have negative 2 squared minus 4 over negative 2 plus 2. Well, this gives me 4 minus 4 over 2 minus 2, which is 0 over 0. That's a problem. I don't know what to do about that. We call it an indeterminate form. And so we can't just compute this limit by kind of just plugging things in outright. So what we do instead is we do a little bit of algebra first. And this is kind of a general strategy for computing limits, because limits allow us to do a little bit of algebra. So I can rewrite this as the limit as x goes to negative 2. This is a difference of squares, which I can rewrite as x plus 2 times x minus 2. Great. So now I have two factors that can cancel. I can cancel out that x plus 2 with that x plus 2. And what that leaves me with is the limit as x goes to negative 2 of x minus 2, which is perfectly fine. I can go ahead and plug things in now. There's no problems. I don't get a 0 over 0. And this will just leave me with negative 2 minus 2, which gives me negative 4. So the limit as x goes to negative 2 of x squared minus 4 over x plus 2 is negative 4. Cool. So it's also worth pointing out that we only really need to do this kind of algebra step if we get 0 over 0 if we try and plug in first. Otherwise, we really don't need to do that algebra step, because we won't have an indeterminate form. We won't have something that we really don't know the answer to. We'll have just straight out an answer, okay? Okay, so moving on to this example, I have f of x equal 1 over the square root of x minus 1, and I want to know what the limit of as x goes to 1 of f of x equals. So I have the limit as x goes to 1 of 1 over the square root of x minus 1. Okay, well, if I plug things in here, I notice that I just have 1 over the square root of 1 minus 1, which is 1 over 0. Now, this isn't an indeterminate form. Our indeterminate form that we care about is 0 over 0. So there's no other algebra that needs to be done. But 1 over 0 is undefined. It's undefined. So we would say that this limit does not exist. So this limit does not exist, right? And so if we can't find a value for the limit, rather, if we've done everything and we end up with something that's undefined, or our left-hand limit doesn't match our right-hand limit, then our limit doesn't exist. So limits don't always exist. So in this case, our limit doesn't exist, okay? So let's move on to this example. I have h of x is equal to 1 over x, and I want the limit as x goes to infinity of h of x, and the limit as x goes to 0 of h of x. So we'll start with this first one here, the limit as x goes to infinity. So I want the limit as x goes to infinity of 1 over x. Let's think about this for a second. So what does 1 over x mean? Well, we can think about it this way. So imagine I have a pizza, and I want to share it with, let's say, 4 people. If I want to share my pizza with 4 people, I can cut it into 4 even slices, each having 1 over 4th as the amount of pizza that I have. Each person gets a 4th if I'm sharing between 4 people. What if I want to share by more people? Well, I can share by even more people by cutting my pizza into smaller pieces. But then everyone gets a smaller and smaller fraction of what I originally had as my whole pizza. In this case, I'm sharing between 8 people, and I have 1 over 8. So each person, in this case, I have 8 slices, will get an 1/8 of the pizza. But notice that if I keep dividing this pizza, the slices will get smaller and smaller and smaller and smaller. So the more people that I want to divide my pizza among, my pizza slices will start getting thinner and thinner and thinner. And so imagine instead of just sharing with 2 or 4 people, I want to share with everyone on the planet. Well, if I only have 1 pizza, everyone basically gets nothing, right? I'll end up with some slices that literally look like this. So we get like nothing. So it turns out that the limit as x goes to infinity of 1 over x is nothing, is 0. Another way to see that is to think about the graph of 1 over x. If you know how to graph 1 over x, it looks like this. And as x goes to infinity, we start to get closer and closer to 0. Okay, so that's another way to see it. Now, the other question is, what is the limit as x goes to 0 of h of x? The limit as x goes to 0 of 1 over x, well, notice that as I go to 0, my x's start getting really small. So I have 1 over something really small. So let's appeal to your intuition a bit, and we'll say like 1/8 is really small. So I have 1 over, think about 1 over 1/8. Well, we know keep, change, flip, it gives me 8. Okay, 1/16 is even smaller than 1/8. Well, that gives me 16. Okay, what about 1/32? That's even smaller than 1/16. So I have 1 over 32. That gives me 32. So notice that as my denominator keeps getting smaller, I get something that's larger. So this gives me something really large. And so this will grow without end, right? The closer I get to 0, the smaller my fractions get in the denominator, the larger my actual answer gets. And so I end up with something that it just grows without bound. So we would say that this limit is infinity, or it does not exist. Okay? It doesn't exist. There's no finite value that this limit is equal to. So there's a little bit of intuition about the limit as x goes to infinity and x goes to 0 of 1 over x. Okay? And I believe that's all I have for you, just talking about some basic properties of limits. If you found this video helpful, please consider liking and subscribing. Thanks.